Hello again, students. This is where we left off. We were just talking about how to get the mean out of the TI-84 calculator. You put the data into a column and you push the stat, an arrow over to calculate, and ask for one variable statistics, and then it will give you the mean at the top, and that'll be shown here on the next slide. If I can get it. Go to that slide, and you see the data being entered over on the upper left, and then the one variable stats under calc on the upper right, and then there's the statistics you get, which shows x bar 3.024. that would be the mean, which is the sum of the x's, which is the second row 30.24 divided by n, which is the bottom row 10. So 30.24 divided by 10 gives you the 3.024 that's shown there in the output of the TI-84. Alright, so now we're going to move on and talk a little bit about the calculation of the spread, a common way to do that, and we will, if you were to, in your mind, just dream up different ways of measuring spread, there's all kinds of ways to do it, but the three that we're going to talk about here in class are the ones that are most commonly used: the range, the interquartile range, or IQR as we will often call it, and the standard deviation. They all have advantages and disadvantages. The standard deviation is the most commonly used one, and until we talk about the empirical rule towards the end of this chapter, it might seem like it's a pain to calculate, but there's good reason why we calculate the standard deviation. It has a very useful interpretation, particularly when we have data that is unimodal and symmetric. So let's move on here. Let's look at an example. This is the daily high temperatures in degrees Fahrenheit at two locations: Provo, Utah, where BYU Provo is located, and San Francisco, California. And those graphs are on the same scale. As you can see, Provo has a lot more extreme temperatures than San Francisco does. That's not surprising. The weather doesn't vary as much in San Francisco as it does in Provo. As such, the measure of typical value, the center of the data, will not be that different in Provo and San Francisco. That's maybe to surprise to some people. Those that know these two cities probably understand that Provo seems a lot colder, and it is in the winter, but it also gets hotter in the summer than it does in San Francisco. So if we go to the next slide, you see that the means are very close to one another. Both the distributions are symmetrical, although the Provo one is not near as symmetrical as the San Francisco one. You see some bumps there, particularly with the high temperatures. However, the center of the distribution is very similar. 67 degrees is the average in Provo, 65 degrees is the average high temperature in San Francisco. I should mention that what we're showing here is the high temperature for the day at each day of the year, and then shown for both locations. So the data is just more spread out in Provo and less spread out in San Francisco. So that's one of the things that makes Provo great in terms of you have seasons where it changes quite a bit from season to season, whereas San Francisco does not change that dramatically from one season to the next. And you can also compare these to a third place, which is Maui. Not Maui, but Lahaina here in Hawaii, where I'm located as I record this video. And you see that it not only has average temperatures that are higher than the statistics for Provo or San Francisco. You see the average is shown here as 83.4, but you can also see that the variability is much smaller. It's much more, all the days are very similar in Lahaina in terms of temperature, but it does get a lot wetter right in the spring, as everyone experienced this year with the flooding that occurred in Lahaina. So that the differences in the typical value and the differences in the spread should be apparent when we calculate them. Also, the range. You see that the range as shown here in Provo was 80 degrees, meaning the difference between the highest temperature and the lowest was 80 degrees, whereas the range, the high minus the low, throughout the year was only 40 degrees in San Francisco. In La Jolla, it was a 9-degree range from the lowest temperature to the highest temperature. So that's what the statistics, the summary data, is telling us when it quotes a statistic like the range or the interquartile range or the standard deviation. All right, so you see the standard deviation, by the way, and the range. These are computed out of StatCrunch, are shown at the bottom of that chart for La Jolla. Now let's go on here. And talk about the standard deviation. So the standard deviation is a measure of spread. It's a measure of how far away the typical observation is from the center of the distribution. We'll use the mean in this case as the center of the distribution. And one interpretation of it is that for most symmetric unimodal distributions, more than half of the data is going to fall within one standard deviation of the mean. And we'll quantify that a little bit more later on in this chapter when we talk about the empirical rule. But you can think of it as a measure of the typical distance of observations from their mean. How far away from they, on average, away from the mean. And of course, the bigger that number is, the farther away the data tend to be from the mean. All right, so in the gas data, where we were looking at an average gas price of 3.02, this is from Austin, Texas. Standard deviation was 0.085. You can round that. Let's just round it up for 9 cents a gallon. So the typical price of gasoline in Texas varied around the mean by about 9 cents, or one standard deviation. So 3.02 plus or minus 9 cents gives you $2.93 to $3.11. So more than 50% of the time you would be in that range when you try to determine what the gas prices are going to be and how much variability there is. Right? So a few things about standard deviation. It can range from 0 to infinity theoretically. You'll never get infinity for a result, but it can be very large. It's always positive because it's measuring a distance, and its size is relative to the data set, what the units are that you're measuring, and it comes out in the same units as the data. So if you estimate it, just kind of, is this going to be a big or a large standard deviation? Don't worry about the numbers so much. The number of eyeballs people have, that should not vary a whole lot from 2. Turns out the average is less than 2. I don't think we have many people with more than 2, but there are people that are missing eyes for one reason or another. So it's going to be very close to 2, and there's not much variability. The number of hairs of head on the heads of on the heads of people in the class, that would vary a lot. We would get a very large standard deviation because it varies a lot from one person to the next. Obviously, if you use my head as an example, it's going to be not very much hair, as you know. Age at inauguration for all presidents of the U.S. How much variability is in that? There is a StatCrunch data set. If you just go into StatCrunch and open some available data sets, there is the U.S. presidents is actually in there. Standard deviation is about 6.6 years. So there's an average, and most people are within a fairly close range of that average. Definitely not a small number, but not a huge number either. And the miles from the sun to the planets in our solar system, the standard deviation there would be huge. The point here is that the standard deviation measures spread, or the amount of variability in a data set. Now, to get a feel for the standard deviation a little bit more, I'm showing you here 6 data sets where the numbers all go from 1 to 8, or about that range. And you see that they range from one down there on the bottom, called labeled F, where there's hardly any variability, to some others that have much more variability. And if you want to spend a little time on this exercise, that's a good idea, just to make sure you understand the standard deviation. So arrange these just by name, from the smallest, the group that would have the smallest standard deviation, to the one that would have the largest standard deviation. You can stop the video now and see if you could do that, and then I will reveal the answer and see if you got the same answers as what I'm going to show you here. So let's reveal the answers. I'll click on this, and you see those are the standard deviations, and the smallest one would be the F, where there's very little variability. The largest would be E, where they're completely spread out from the lowest to the highest, so half the data is at the low end and half is the highest. And the one that is maybe closest to F, which has no variability, is D, because the data is gathered around the middle and there's not as much spread. There's observations out at the extremes, but not very many out at the extremes. So at the top of the page, they're shown in order, F, D, B, A, C, and E. And hopefully your intuition told you something close to that, is the ordering of these data sets in terms of their standard deviations. Let's move on here. And this is the distribution of the amount of particulate matter, or smog, in the air in 333 cities in the United States. So it's environmental data, and the average of this data is 10.7. How much spread is there? Well, it turns out the standard deviation is about 2.6 micrograms per cubic meter. So all of these are in the same units. The mean is in micrograms per cubic meter. It's measuring how much of these particulate matter is in the air, and then how much variability there is from city to city to city, and the standard deviation measures that. Now, one other piece of information here is that let's just go one standard deviation above and below the mean. If we do that, we get 10.7 minus 2.6, which would be 8.1. And going above it, we get 10.7 plus 2.6, which would give us 13.3. So in that range of 8.9 to 13.3, more than half of the data would fall. So the EPA says that levels over 15 become unsafe. So how much of the data includes cities? How much of the cities are over 15? Well, you see the blue line there indicating unsafe levels. There are a few cities above the value of 15, and we could calculate in standard deviation units how far above that average of 10.7 15 is. We take 15 minus 10.7 and divide it by 2.6. That would be 4.3 divided by 2.6. That's approximately that's a little more than one. It's about 1.6 or 1.7. I'm doing this in my head, but it's more than one and less than two standard deviations above the mean. So we have some data that is above 15, but it's not the predominant. It's not the biggest part of the data. So the 8.1 to the 13.3, I may have said 8.9 earlier. 8.1 to 13.3 is the typical range of data. And down here it shows that most of the cities are in the safe range, but there are a few examples of cities above that. This is the formula for the standard deviation. And at first it can be rather intimidating, but when you work through this a time or two, you realize it's not that scary. It's a summation, just like the mean is a summation of all the values. We're summing the values minus the averages. So you see that X bar in there, that means the average. And we take the distance of each point from the average and we square it. When we square a negative number, we get a positive. So we get these numbers will all be positive. We're going to add them up. divide by 1 less than the number of observations. We used n for the mean. For the standard deviation, we use n minus 1. And we take the square root of all that to give us the standard deviation. I'll stop right there and we'll come back in a minute.